So with no further ado, we will actually introduce Ed Fong and move on with the presentation.
Thank you very much. And so I didn't get your name, the woman that introduced me.
Oh, sorry. My name is Trisha, K0TRD.
Okay, Trisha, thank you very much. So I imagine, let's see, I see the audience there. So good evening. Raise up your hands if you have one of our antennas. Quite a few. Okay. Well, that's kind of bad for me. That means I can't sell you anymore. Oh, gee. Yeah, I like it when nobody has our antennas. Wow, do I have a potential audience? No, we'll do fine. Yeah, so I teach over at UC Santa Cruz, and this is how we raise funds. We sell these antennas for my students, and I actually tune every single one. We've tried, we have it in our class where they build it, but then for tuning and putting it in assembly, I do all the assembly. So they basically make me all the components, and this way, because my students only last 1 and most 2 years. So you can't track them or anything. So I figured, no, I'm responsible for every single one. So every single antenna that is sent out, I've actually put on a network analyzer and tuned it myself. Okay. So yeah, I've been a teacher for 30, 40 years now. I teach I'm down to 3 classes. And they're all graduate classes, which is kind of fun. I teach a RF wireless class, really related to ham radio. Antenna class, really related to ham radio too. And then I have an optics class. That's not as related to ham radio. High-speed optics and high-speed wired communications. But yeah, we still use the Smith charts and things like that. And then a lot of my students become hams. I tell them, a lot of them, it's really an RF program, RF wireless program. But I always tell them, if you like this stuff, you should get your ham license. And because a lot of them come in with their ham licenses. And I give you a good number of, over the 20 years I've been at Santa Cruz. Yeah, it's 2002. Yeah, 20 years. The ham clubs that I'm involved in, I would say a third of the members are former students of mine. A third of the members and board members are students, which says if you want to grow your club, you have to open it up to everyone. Just, you never know. So I've had, I'm sure, 1,000 students over these years, and I guess I've got probably at least 15, 20 real diehards now. They work in the industry and they come to the clubs and they give talks and they get really involved. But that's out of thousands, not, I don't know, thousands, but 1,000 students probably. You never know. You have to open it all up to everyone. They either get hooked or they don't get hooked. They're what we call roped in. That's our terminology in our club. Let's rope them in. So, okay, especially with volunteers, right? You gotta, it sounds like we have the same problem you guys have. And I don't remember this when I was growing up. People actually would run for president. Now, who wants to volunteer to be president? Here, you raise your hands, you blink your eye, you're it. It's like during the swap meets and things. You look at it, you own it, or you touch it, you own it. Okay. Anyway, let's get started with this dual band antenna thing I'm going to talk about. So what I'm going to talk about tonight, this is one of a series of about half a dozen lectures I give. This is one on antennas, and we just give a bunch of other ones, mainly because I wrote about because people needed ham speakers for their clubs. I know how bad it is. I am responsible for 50%, or I'm with a partner, Steve Stearns, getting the guest speakers every month. After a while, you use up all your network of friends, and you have to start hunting around for speakers. So I know how hard it is to get speakers after a while. And the people do not like me to start approaching them at big meetings. Oh, he wants you to speak. Oh no, run. So I know how it is. Anyway, okay. So tonight I'm going to talk about one of the 4 lectures on antennas I give. I also give one on DMR. I give one on the USDX radio. Oh, and I give one on op amps. And maybe a few others. There's a lot of it is the notes from my graduate classes. I take away all the math and just try to see if I can explain it without the math. That's also a good challenge for me. So I'm going to talk about how do you make a dual band J-pole. You folks probably made single band J-poles, a lot of plans, but a good dual band J-pole, that wasn't so simple. And what I'm just going to discuss is I first introduced this back in 2003 in QST, and then a roll-up version was in 2007. We did a tri-band version with my daughter in 2017. And then the AWRL has copies of our antennas, I think at least 2 of each, and they've tried it out, tested it out, and said, yeah, it's a pretty good, simple configuration. And in fact, this weekend I found out from, you guys probably know Tom Schiller over at Force 12. He was telling me, it was strictly accidental that I use all copper in my antennas, all copper wire. I know it oxidizes, but it's in the PVC pipe. He says, you're good, copper. We tried out. I didn't know this. I mean, I knew there's a difference. For an antenna, do not use chrome. Like a chrome whip. Do you guys raise your hands? You guys know who Tom Schiller is at Force 12? Raise your hands who knows Tom Schiller. He is the founder and owner of Force 12, the Force 12 antennas, the very famous beams, HF beams and all that, and the D expeditions. So I don't know him real well, but I know who he is. He knows who I am. But yeah, I'm glad he does some of these experiments. It turns out that, like these whip antennas with walkie-talkies chrome, you measure DC wise, it's low impedance, 0 ohms. It's pretty poor as an RF radiator. He characterizes, with a drone and measuring, actual measurements, not SWR. SWR we can get low anytime, but how well does it work? It turns out that the best material to use, for an antenna, for the efficiency, is copper. Don't use stainless steel and stainless steel whips, not chrome for telescopic antennas. What else can you use? Stainless steel, zinc, any of the other, aluminum, terrible. He says terrible. You actually measure the RF performance, not the SWR. That just tells you the match. But it was interesting. Yeah, no wonder my antennas work fairly. And everyone tells me this, when I sell it to you guys, your antenna somehow works really, really well. Now I know. It's because I use copper and all my stuff. It's all copper. It's interesting. But anyway, I'm going to talk today about how you make a dual band JPO. And pretty well documented. This is the QST article here in 2003. Here's the dual band version in 2007. Here's the tri-band version. Here's my daughter when she was young, 7 years ago, almost 7, 8 years ago. She's got her master's in mechanical engineering and a master's in mechatronics. Some people know robotics. She knows a lot more than I do with all this modern Arduino and all this stuff. That just beyond me, beyond me. That's her the tri-band antenna. So that's a talk I give. How do you get 2 meters, 220, 440, all in one antenna? No radios, no lightning arrestor needed. Works really well. And it was done on a contract actually from FEMA back in 2012. And we came up with this. Their cost is about $50. We sell it to clubs for 60, and it retails for 95. So it's a pretty cool antenna. Took me a while to design it, by the way, given the requirements. They want no radios, they preferably no lightning arrestor. I mean, the only requirement that wasn't so bad was, they didn't want it too tall, about 6 feet at the most. What was the only requirement? Oh, that its performance didn't have to be super, but pretty good. I go, well, that makes it a little easy. It didn't have that 10 dB. So anyway, and talk about patents. I am not a patent person. I just like free flow of information. But after a while, you do have to patent these things because people steal these ideas, and a lot of this is university stuff. So my first antenna, the one I'm going to describe to you today, not patented. I just didn't dawn on me to patent an antenna. But when we did it and published it in QST, a lot of copycats that were selling them on eBay, making them, and then we started buying some just to see, and they weren't very good. They just copied our dimensions, and they didn't read our articles very carefully, saying it's not the dimensions, it's the wavelength, and the 2/4 wavelength that UHF or VHF differs in different materials. The only standard you have is air. You have air, usually it's constant, but it's air. You can't make an antenna out of air. So any type of material has a velocity factor. And a very 1/4 inch here, 1/2 inch there. None of them were tuned. We bought like 3. In fact, I didn't buy them because the people recognized my name. I bet students just go buy this one, go buy this one. Not a single one resonated on the ham bands. 150, those went on a weather band. They just built it to our dimensions on material they just picked up from the internet. And in fact, the materials are so important now that years ago we said, we just can't buy the material online. we've got to go to the manufacturers to order it directly, special order, to make sure the velocity factors are consistent, you know, the density of the plastic or the dielectric. Because it varies a little bit. The dimensions are going to vary. Not that you can't fix it, just that you don't have time. I'd rather put the weight on the manufacturer. You make this twin lead or whatever it is coax, and you're saying it's got a velocity factor of 0.8. And if I always buy it from you, how much tolerance can you give? And 2, 3, 5% at the most, I'll accept that. But if you buy from different manufacturers, the velocity factor would vary. Probably 10, 15%. And then you have to retune. And so we buy from Seminole Wiring. We buy our coax, our RG174 Maya cables. So we keep it very consistent. There's a long story behind cables. Because what we need, we're using them for matching. If you're just using coax for 25 feet or so, that doesn't matter. But if you're using it for matching, sure, it's going to vary quite a bit. So, so about the patent. So our lead attorney, Mike Kaufman, I think Mike Kaufman, our lead attorney, said, no, you got to patent this stuff because people are going to copy it, and we got to protect it. So we started patenting our tri-band, our gain J-pole antenna. So that's another lecture that I give on the J-pole. How do you really get gain? It's nothing that simple. It's actually pretty complex. Real gain that you can measure. So Mike says, now you got to patent that. So we couldn't patent the antenna we talked about today because it was just too late. And sure enough, he's right. When you patent things, people don't copy you because they're afraid you're going to sue them. Disadvantage costs you about $5,000 every patent. It's kind of a hassle. That's why I don't believe in them, but you have to. You have to kind of protect yourself. Okay. But if you have questions, just wait till the end. In a Zoom session like this, it's better to have a dialogue conversation at the end. Just jot it down. I know how sometimes it's hard. You forget the question. Just jot it down. Okay. If I were to build an antenna today, why would I use a J-pole? At VHF, UHF, it's a very good choice. No radios. J-pole can have no radios. Nothing sticks out. The wind load is very, very good. It's actually very close to an ideal pattern, better than a ground plane. A ground plane does not give a dipole ideal ground pattern. It's a good one, but actually a dipole gives a pretty good one. And plus it's end-fed. And yeah, it's a little longer, of course. You guys probably know that. But a VHF, UHF, not so bad. I'm amazed that they adopt. Well, they put that an end-fed HF antenna. They put a 49-to-1 transformer to shorten it. I guess you can put a quarter wave coax, but then it's too long. But even it's configuration like that, pretty lossy. In this case, we actually use a coax to match it, or a twin lead to actually match it. So the loss is pretty low. It's not zero, but it's pretty low. So this idea of this J-pole. Everybody practically uses a J-pole configuration now. Here's a big tower called Sutra Tower in San Francisco. It has all these communications antennas on it. It's got a couple of dozen up there. And I can't see us. Years ago, I would hike up there when I was a kid. You expect an antenna. It's a ground plane. You see radio. You see a center conductor, and you see radios. That was pretty standard when I grew up in the 1960s. And you would build them out of an inverted SL239, get some copper wire, and some people call it hanger antennas, make them out of hanger. The problem is solder didn't stick to them as well, but you can make them out of copper wire. And you can get to SWR though. Does it work? Hits a repeater. I mean, I didn't have a spectrum analyzer to measure the performance. All I had was an SWR meter. SWR meter says, 1.3, 1.4 to 1, good enough. And you think it performs well. Well, it matches well. It doesn't mean it performs well. It matches well. So that's all I knew. But these days, the J-pole configuration will show you today, and I'm sure a lot of you know this configuration. You probably tinkered with it. It's actually used commercially almost everywhere. How do you know? There's no radios. None of these. I don't see any radios, and they're all pretty tall, right? Because a J-pole is usually 3 1/4 wavelengths, piece of stacked. A ground plane, if you just want one element, the VHF, for instance, it's only about 18, 19 inches tall with radios. I don't see any of those here. The equivalence of that would be 3 times taller, but no radios. And I think a better matching network and better pattern, so better antenna. And again, at VHF, it's Reasonable, right? These are reasonable. Their heights are reasonable. You couldn't do that on HF, but at VHF, yeah. And at UHF, even better. At UHF, quarter wave is 6 inches. So you have 3 of them, so 18 inches, no big deal. So you can implement this J-pole configuration at VHF, UHF here. Very convenient. See, the old days, you guys probably know ground planes, and we used to build these dipoles. We didn't know any better. I wasn't an engineer back then. I was just a ham in high school. Copper pipe, that's just a pure dipole. There's a little Teflon insulator there that you don't see real well. And then you have coax coming out like this at 90 degrees. It has to be at 90 degrees, otherwise it'll change the resonance. Again, we didn't know any better, but this is not a, I mean, if you can actually implement this, it's a good configuration. It's a halfway radiator. So is the J-pole. But why is this not good? Not that it doesn't perform well. It's too inconvenient. It's center fed, 90 degrees. The coax got to be 90 degrees. If it isn't, starts resonating and it causes havoc. And then it works, the further you get this out, the better it works because it's away from objects. Right? In a J-pole, it can be right at the top of a tower and there's no interference. But worst of all, what we found was, I don't have a welding torch. I've got a solder pencil and a little blowtorch. That just can melt solder. And you guys know solder, pretty soft. And you think it's a metal. It's a very, very soft metal. You can flex it. So even if you melt it, it doesn't get any harder. I mean, just here, you didn't weld it. You soldered the T section here. You solder this here. Are you kidding? When wind vibrates this over a season, if it's a windy area, that breaks right off. That solder is way too soft. You're bending it back and forth. I mean, if it's static, it's fine. And what's worst of all is you want this to go further and further out. It works better because then this mass here doesn't disturb the pattern. Mechanically, it's terrible. The further you get this out, you get an R cross F or a torque. Right? This moves a little bit. It puts a lot of force on that. And not to mention the vertical force. You can put a lot of vertical force here. You've got to multiply it by the distance. And that's basic mechanical engineering. You can hold this if you're standing here. You can hold something to your hand really close, but if you stick it out, you really feel the force because it's the torque force or R cross F. So it's not very practical to have this really, really long. It'll break right off. You want this as close as possible, but that's terrible for the pattern. So overall, this is not an optimum antenna to use. I say optimum because it still works, and hey, we used them. We didn't know any better, but we know a lot better now at 40, 50 years later. There's better configurations that just can run circles and not only electrically, but mechanically. So this is mechanically a very unstable antenna. I mean, you see the commercial people working on this, they don't use solder all day. It's all welded. I agree. If you want to go buy yourself a $5,000 welding torch, fine. But most of us don't have that. So we want good performance with tools that we can make ourselves. So I like the J-pole. Why? Sometime in the 1990s, I think Denny Monticelli, A6C, introduced it to me. I played around with it. They were using cheap Radio Shack twin lead. I said, hey, for cheap Radio Shack twin lead, which, by the way, back then was like $1.49 for 50 feet or so. Pretty cheap stuff, though. And I started putting it in, hey, this is pretty good. It actually works. I could tell already without sophisticated instruments, it worked better than a ground plane. And when you quantify it now, it's actually about 1.6 dB better than a ground plane. So, I mean, it's not night and day, but if it's scratchy, if a repeater scratches your person and then you use a J-pole, it'll clear up. But then he gave it to me in a roll-up form, single band by a single band. And I said, this is really cool. Yeah, I played around with cheap hanger antennas. When you're 20 years old, you really hesitate to go spend, even back then, $60, $70 for a really good base station dual band. What did I get? That Ringo Ranger. Ringo Ranger, probably a lot of you guys know about it. It works well. It's just a piece of junk physical. I mean, it's just too many connections and all this. And it fell apart after a few years in the wind. So I like this idea. I said, well, this one's so simple, I can stick it in a PVC pipe. And so it'll be all covered and protected. And I did. You have to readjust it now. I was kind of disappointed. I stuck this antenna into a PVC pipe, and I got an SWR meter in it. Resonated way lower. And then I thought about, problem is the PVC pipe is slowing down the speed of light. Because all these antennas, all antennas have to behave C equals F lambda. Right? The speed of light is always equal to frequency times the wavelength. So in air, that C you could use 3 times 10 to the 8th meters a second, and then calculate 145, 146 megahertz. Lambda, the wavelength is about quarter wave, about 18, 19 inches. But if you stick it in a PVC pipe, you can't use that C 3 times 10 to the 8th meters a second, the speed of light anymore. It slows it quite a bit. It's 3-4%. Right? Because whenever you put something in front of anything, it's going to slow it down. Certainly you're going to speed it up. The speed of light is the fastest thing we know for traveling. So when you put that antenna inside PVC pipe, this ribbon antenna, the resonance will drop. If you don't do anything to it, the resonance will drop down like 142, 143 megahertz, not usable. But after I figured it out, you just retrim it. You just got to, once you retrim it, so what you'll notice is our antenna that goes in the PVC pipe and the one that's designed just to be rolled up and hanging, it's quite a bit. It's a 2-inch difference. So you cannot interchange them. It's too much to be interchanged. 2-inch difference is quite a bit. So anyway, my feeling was, hey, if I can readjust this thing, put it in a PVC pipe, it'll be a real base station antenna. And PVC is really well protected. You can really live on that, right? It's not a piece of junk at that point. And then we've as of today, we've sold well over 40,000 of these things in the last 20 years at for my school. 40,000, but we have, you say hams? No, not all hams, of course not. But we have contracts with FEMA, a lot of commercial, police and fire. Our biggest customers are ATD alarms. They use a mesh network. They buy the UHF one a lot. So yeah, we're doing quite well. I think the students like it. We make pretty decent money, I think, for them. Let's see what else. Let's say. So how about the dual band thing? So in the early 2000s, it was to a point where you go down to ham radio outlet looking for a new radio. At that point, you can afford for like $50 more, your single band 2 meter. Let's say you're looking for 2-meter FM radio. And the guy at HR said, "Yeah, we can sell you one, but for $50 a lot more, get UHF." And handy talkie difference is even less. The CS580, what was it? The Yaesu 470. I mean, it was a little bit more than a single band, but not like having to buy 2 radios. So that quickly became very popular. As soon as the commercial manufacturers started putting dual band handy talkies, dual band mobiles, and then we started getting a lot of UHF repeaters. Why wouldn't you? You can go out and buy a new radio. Why not get a dual band? I mean, yeah, it's a little bit more, but not like 2 radios more. But then you needed an antenna. Well, the first thing I know, not me, but my friends noticed, they're using their ground plane or their Diamond, well, not Diamond back then, but Larson and Ringo Rangers. Yeah, but my Ringo Ranger kind of works. And I looked into it and said, well, yeah, that's a good way of describing it. Kind of works. What's good about it? The good about it is the SWR is still reasonable. And there's a good reason for that. All antennas resonate also at their odd harmonics. In other words, if you make a 100 megahertz dipole and you get one of these cool little $95 VNAs, you'll see it obviously dip at 300, 500, 700, etc. at its odd harmonics. So that's why at 145 megahertz, 146 megahertz or so, your VHF antenna, you put like a nano on, okay, with dips, multiply it by 3 at 430 to 450. You'll just a single band 2-meter antenna. You'll see a dip. Say, wow, cool. The antenna should work. Well, not really. Let's get good SWR. Right? Don't confuse working with a good match. Good match is necessary, but what a mathematician would say, that's necessary, but not sufficient. Just because it matches that, yes, you need it. That's good, but you're not finished yet. Well, it turns out that when you use it as a third harmonic, I think a lot of you guys know this. If you've been a ham mom, you lose about 6 to 8 dBs. That's pretty bad. I mean, all of a sudden your 4-watt handy talkie looks like a 1-watt handy talkie. And I've measured this. Use one of my antennas at UHF. You might just leave the rubber duck on your handy talkie. It's about the same. So that's pretty bad. But why does it do this? Let me show you the pattern. Here. See, here's a simple easy neck pattern. Here's the sky. Here's below the sky. And let's say this is sea level. So typical is, you stand here, and this is the horizontal. You walk out here, you go further until you don't hear the guy anymore. Well, if you're transmitting here, what EasyNet says is if it's a resonant half-wave dipole vertically, the pattern will look like this, figure 8 pattern, or when you look from the top, it's like a donut. So 360 degrees coverage. Now, it doesn't cover the sky very well. That's good. That's actually good. You don't want like a hemisphere pattern. You want this pattern because it nulls right up to the sky, and its peak, ideally, is right at sea level, from the horizon. But now, if you took that antenna, in this case, 2 meters, 146 megahertz, and went up to the third harmonic, 445, right? 435. That'd be 435, 440 in that range. Because if it was 150, it would be 450. So about the third harmonic within the handband. Again, the SWR will be okay. But if you really to simulate it, or if you have the ability to measure it, although you don't have to measure it entirely, you just experience it. Hey, it doesn't work very well. I'm not quantifying, it just doesn't, I can tell it's not working as well as a rubber duck. Well, the reason why, if you quantify it, is that a third harmonic vertical antenna will look like this, the pattern. In other words, it's about 75% of the energy that you generate from your handy talkie or whatever goes up into the sky. And only about 25% of it is here. So now I've convinced you, you've got to get away from it. You're not going to use a 2-meter antenna on 440 unless your life depended on it, right? Oops. The good news is it doesn't blow up your radio. The bad news is it doesn't work. Uh-oh. Doesn't have to call me back. Hello? This is Ed. Hey, I'm in a seminar right now. Yeah. I get calls all the time. It's okay. It's another ham. I get phone calls from hams all the time because I'm a ham, right? Why not? So anyway, back to this. If you quantify it and say, what's going on here? It's because if you use an antenna at its odd harmonic, the first odd harmonic, 75% of your energy just goes up into the sky. Great for working satellites and the International Space Station, but not good for talking to your friend here or even a repeater. So the idea is, can we get rid of this? Can we, in a single antenna, make this UHF, which is the third harmonic, not look like this, but look like this? And we did it. I believe we did it. I mean, all the indications are, we've sold enough of them, everyone says, yeah, it's right, it does work. So the goal of this was, here you got this 2-meter J-pole, you make it also UHF, and it's got to work well. Not only does it have to work well, whatever your clever solution is, it can't involve, exotic inductors and capacitors. You can't put a capacitor at UHF. Some of you ham guys will know this. You experienced VHF, UHF people. It's hard to specify a capacitor at UHF. Usually the value of it is measured at some frequency, 10 megahertz or whatever. By the time luckily we have all these network analyzers these days. We can tell you how bad the capacitor is at 450 megahertz. It's got usually some series inductance, a lot of series resistance for losses. They're terrible. So I figured, and even if I found one, I said, and this requires 6 picofarads from here to here to get the antenna to work. Well, you buy it from a different manufacturer, at those frequencies, it would behave differently. If it was HF, yeah, you can get away with it, but not at 450, 460 megahertz. So no capacitors, inductors, the same reason, because they're all not easily reproducible. So I given those constraints, I tried all kinds of different configurations. So here, brother. So here's the J-pole you start with, twin lead. Well, the only thing you guys got to know, I think you guys should know this if you're experienced ham. Here's a Smith chart that explains a lot. A Smith chart says if I start out with a short circuit with a transmission line, and if I go over a quarter wavelength, it should be an open circuit. Now, unless you study for your extra class and you're really into this, it isn't intuitive. I mean, I had a hard time getting this concept originally because you think of, you take a piece of coax, like I have right here, it's 5 inches, which is quarter wave at UHF. You think of it as just a piece of coax. No, it's trickier than that. It says if I short one end, if I short circuit at one end, most people say, if I short circuit at one end, what's the other end? That's a short circuit. No, it isn't. You experience hams and RF engineers. No, it is not. At DC, it may be. At DC, because we're all used to thinking in terms of DC. DC, if this is a short, that's short. I totally agree. That's an open, that's open. That's a DC. But as soon as you get into AC, things start flipping. And this is what I say to my students. They go, what do you mean? Well, I'll give you a perfect example. If I have a block of wood, insulator, I just ask, insulator or a conductor? They virtually all say insulator. You're correct. You're correct at DC, but you're incorrect at AC. And I shouldn't have to pull out any instruments. Radio waves. Wood doesn't stop radio waves. You walk inside your house, it might attenuate them a little bit, but it doesn't stop it. It conducts pretty much right through. So wood's a good example. At DC, it's an insulator, but it's a conductor at RF. You can't depend on wood to insulate you at RF. And then the other extreme is aluminum foil. Aluminum foil, conductor or insulator? And most people would say that's a conductor. It is at DC. So you can't confuse the two. At AC, it's obviously, we use aluminum foil as a shield, as a Faraday shield. What's a Faraday shield? It's a technical name for an insulator, RF insulator. It blocks the RF. So if you can kind of keep that in mind, they're almost direct opposites. So again, with transmission line, if I short it on one end, at a quarter wave, it will be an open. And if it's an open on one end, this is harder to imagine, but open circuit one end of a coax, it's a short on the other end every quarter wavelength. So they'll occur at different spots or different frequencies. So at UHF, this happens to a UHF stub. An open here becomes a short. If I short this, it'll become an open. And you can measure that on a network analyzer like a nano. Hey, another show of hands. How many of you guys have a nano? Quite, man, that's pretty good. That's really good. Now, isn't that a cool device? You're lucky you didn't go buy, an MFJ years ago or the AEA, also come out with this nano full network analyzer, $100. What a steal. That's what I say, man, what a bargain. I would have loved one of these when I was growing up. And in fact, in our lab, we have an 8753 that you can't haul, you get to go fix a repeater. You can't haul that thing up. You'll probably break it by the time it jars, around in the mountains and all this, riding on a trailer. You probably break it. But these days, boy, that is amazing. You live in a world-changing world that and network analyzers, because this one's a 1.5 gig one, for under $100. Unbelievable. I wouldn't believe it. So anyway, that's the Smith chart. That's the only thing you have to know. A stub, a short becomes an open becomes a short. So here's how, I'm just going to explain to you without the math, how a J-pole works. This is a twin lead, so ignore this part. It's just twin lead cable. Ignore this part. Here's the actual active part, 37, 38 inches. That's a half wave at 2 meters. So normally you would have center fed this because there's a low impedance in the middle, right? It would be just this one we showed. That's that 38-inch, 37-inch piece here. And right in the middle of it is a low impedance point, typically 75 ohms, which means it'll match the 50. It's low. But if you look at a J-pole here, it's still low here. But again, I explained to you, when you feed it, it's so inconvenient. It's just not gonna hold up in harsh weather. I know that. We built a bunch of these and we're frustrated after a few storms, the thing wouldn't work. You need to change the configuration. So here's a good one, end feed it. Where's the problem? Here's just a low impedance in the middle, but we can't do it there because you have to feed it at right angles. But as you go further off center, all the way a quarter wave down, even a quarter wave up here, it becomes a high impedance. That's why an antenna radiates. At the tip, it's a high impedance. This is high current, low voltage. As you go up further here, it's high voltage, low current. That's where it radiates. But where it radiates low current, high voltage, that means it's high impedance. How do you feed energy into this piece then? You must need a high impedance to match it. How do you get high impedance? With a short. A quarter wave stub, like what I showed you in the Smith chart. If it's shorted, it becomes a high impedance at the end of that transmission line. So therefore, kind of high meets against high, and we do it fairly efficiently now. By experiments and all this, we do it fairly efficiently, and it does work. End-fed antennas are based on this at HF. J-poles are based on this principle at BHF. So people have tried different ways. Oh, in my case, how do you feed it? Here's a short circuit. Here's a high impedance. So here's kind of like the plot of the voltage, right? Obviously, at the short, the voltage is going to be 0. But as you go to higher and higher impedance, the current will go down, but the voltage will go up. And theoretically, it should peak at a quarter wave. And again, I want to remind you, you see this quarter wave here. It's 15 1/4 inch, 1 1/4 inch. Add it up, 16 1/2. Shouldn't it be like 18, 19? It would be if it were an air. This is not an air. This is in twin lead. It slows down the speed of light. So instead of using 3 times 10 to the 8th meters a second, I use something like 2.6, 2.7, because it's in the twin lead. The waves don't travel the speed of light as you know, like an air. It slows it down by maybe 15%, 10, 15%. I'll give you a good example so some people remember. When we place antennas into human bodies for these low transmitters and things like that, water has a velocity factor of 0.5. In other words, it's typically twice, or it's got the density, let's see, you can't say it in percentage. The density in water is equivalent to 0.5, which means whatever antennas you resonate at air, you have to cut in half. It's going to go in the water or go into your body. The antennas you put in or cut, it's half the size, which is pretty amazing. We know, obviously, engineers have known this for years and years and years. Yeah, you just can't go, oh, this walkie-talkie works great, we're going to put it underwater, and all of a sudden the efficiency doesn't operate anymore. Yeah, it's got to be about half. Theoretically, it should be half the size in water. So that's why when you drive the thing on 2 meters, the actual quarter wave stub is no longer 18, 19 inches. It turns out to be about 16 1/2 to be matched. Also, you match here, and here's the kind of like the voltage waveforms. Obviously, with a short, it's going to be 0, and then up here it's going to be high. And where do you tap it off? You have 50 ohm coax. Well, this is short circuit, and that's high impedance. Turns out about 1 inch, about 50 ohms. They're close enough. It's hard to get it perfect, but it's close enough. I mean, if you guys have used these J-poles, they work fairly well. So that's how a basic 2-meter one works. How do we get it? Okay, so a lot of versions of this, right? You see copper J. We make them in the lab here. In fact, I have one. This is the one we spend 1 session of lab. We make these. The students make these that just show the matching or how it works and how it doesn't work too. Because this configuration, you guys probably have them. But you guys have mine now. Might work better. So it's based on the same principle. Here's the half-wave radiator, but you make the transmission line out of a right angle, an elbow, and a T. And you make this transmission line, and the tap is, this one shows about 2 inches. It should be, typically it's lower, but anyway. They tap it off, and what's the problem I see with this? At VHF, you probably can get away with it. At VHF, it is pretty much at the max, because this is acting as a transmission line. VHF quarter wave, 18 inches or so. And here it is about a little under 2 inches as a transmission line. Remember, it's got to transfer the 0 ohms to a high impedance. And it gets away with it. When we measure it, it gets away. You lose some of it here because to jump across to make the 50 ohm tap, you're exposing the center conductor. And also at the 90 degrees of where you want to radiate. So it's radiating in a wrong pattern, plus you're getting losses. So you lose about 15% here at least at VHF. At UHF, it's not usable. This antenna is not usable at UHF. Nothing about this antenna tells you UHF. Remember, at UHF, about 5-6 inches for quarter wave. This is already 2 inches. It's going to radiate in the wrong polarity. It's horizontal, not vertical. So this configuration does not work very well, or pretty randomly at UHF. But at VHF, it works well. I think my number one reason why you wouldn't want one, it isn't dual band, and it's made of copper. So I think maybe 20, 30 years ago when this design was introduced, it was pretty good. But now you go check the price of copper, you can't afford it anymore. So today it's been obsolete because the copper is just way too expensive. There's another one, Arrow puts this one out. They knew they had the problem of the resonators. You know, here's the 2 meter one, and they knew that at UHF it would have a bad pattern. So what they configure is at UHF, they've got a separate J-pole antenna. Here it is, 6.5 inches and 19.25. This handles the UHF. This handles the VHF. I think pretty clever idea. Not perfect. We bought one of. These are hard to build, so I didn't build one. We just buy them. We buy them. It looks like this. We put them together and see, does it work? It does a little bit. So what they did is a UHF, it goes through these two elements. At VHF, you use these two elements. And they have just like 1 feed point. Well, what we found was that's not the optimum point. So you lose a little bit because it's matched at VHF, only this long 57-inch piece matches with this 19.25. But at UHF, it sees this J-pole, this mini J-pole here. So the matching network for the VHF now becomes the main radiating element for the UHF. This is very convenient. Right? It's a third harmonic. So this is half wave here, down here, another quarter wave. At VHF, this is a quarter wave matching right here. So it works out really nice. But you can use this VHF portion just by adding a little piece of 6.5 inch to make also a UHF. But where's the flaw? I mean, I think clever. I'm sure it's patented. I've looked at. I'm sure it's patented. The flaw is here. If it matches to both VHF and UHF, at UHF, half the energy will go into here because it's a match. But also, it's a match here, so half the energy goes there. So without the math, you can conclude half of it's going into the right antenna with a good pattern. The other half of your energy is going to one where you have 75% of your energy spraying up in the sky. So is the thing an improvement over just a J-pole being used at UHF? Yes, it is. Have you totally eliminated the problem with the third harmonic radiating at VHF? No, you haven't. You've improved it, but you haven't. Okay, the next one I have is, I think, anything you hear about a Slim Jim, I've not been able to prove that it works any better, but the good news is I haven't proved that it can work any worse. It's a 2 meter. If you buy a Slim Jim at the swap meet or build it yourself on the plans, Slim Jim's a Slim Jim. It's basically a 2 meter J-pole. Just by tying the piece of wire on top there, we see no difference. Even when you simulate it, just a little bit of pattern difference. It's not significant. I'm not obsessed about educating people that this isn't a good antenna, but I tell you who was, Larry Seebeck, Dr. Larry Seebeck. Man, he was so angry that people were, and he was, oh, just tie this little thing together and get 6 dB. And he said, well, no, you don't get 6 dB by doing that. And he knew antennas, Larry Seebeck. He had he passed away a few years ago. He had a whole website devoted debunking this, saying it's just a 2 meter J-pole. It is. I would agree. That's all it is. You don't get 6 dB gain out of it or anything like that. So beware of that. Snake oil, please. Snake oil. Because to really get gain, I'll show you to get gain. So I got obsessed with it. Then how do you get gain? You have to do something like this. I'll give a talk on this. We make a 4-element version of that, and even then, trying to phase all the elements just right. They say you should get about 8 or 9 dB. I don't know. I can measure maybe 6.2. That's quite a bit, and we try really hard. Every element on a network analyzer and all this, and you get gain. Yes. This one is a 2-element basically. If you get about 3 dB over a single antenna, we can. The first time you do it, you can. But remember, you have to, every time you want 3 dB of improvement, you need to double the number of elements. So it gets to a point of diminishing returns. When we find that 4 elements is about all you can do. But we actually make one. I don't charge for that one. People need them for repeaters and whatever. I'll make you one. You guys try it out, and people like it. It works. I mean, it works as well as your commercial antennas, because that's commercial antennas use a configuration like that, usually or some form of that. It's hard to go buy one of those 4-bay dipoles and with the matching harness and all that. It's just too cumbersome, and they break. So anyway, back here. Okay. So what did we do? We did this. Here's the trick. Okay, raise hands. Who are among the audience? How many of you already know this interesting technique? You guys don't read QST? Oh. Okay. Well, okay, I'll explain it. We explained this in QST. And no math. You should be able to understand this. So I didn't invent this, right? I didn't invent this. This is a J-pole with twin. In fact, Danny Monticello gave me one. Half-wave radiator. The whole object is you end feed it. The only way you can end feed it is high impedance. So you get this quarter wave stub. Short circuit quarter wave will also be in high impedance. And then how do you feed it? You feed it with coax about 1 1/4 inch high, right? This is 0 ohms, and that's infinity. Turns out 50 ohms is right at about a little over an inch. Really convenient. And if you guys ever use these J-pole configurations, pretty good SWR. But remember, just because you have good SWR doesn't mean you have a good antenna. More than likely, you have a good antenna, you probably have good SWR. So having good SWR is necessary, but not sufficient. So what did I add to it? Got to see where the problem is at. Here's where the problem is at. It matches. Remember, I said the VHF J-pole worked. It didn't. Good SWR didn't blow up anything at UHF. It's just that when you start using this, but it doesn't work very well. Let me explain to you why it doesn't work very well. Well, let's first step. Why does it match? It matches because of this. This configuration matches at VHF. And if you map the electric field in this, it looks like this. Obviously, a short is 0. And to get high impedance, it peaks out at a λ/4, a quarter wavelength. If you were to map the voltage, or you're driving this with a carrier, it looks like 0, and then you move the meter along between it, it'll go up, and peak out there. And it's high voltage, it's low current difference, a high impedance. High impedance matches well with the dipole that's in there. It works. That's basics of an end-fed antenna. So what happens at the third harmonic, just without the math? This is how the pattern looks. Third harmonic, 3 times higher. Right? Short circuit, can't deny it. Short circuit, 0 volts, right? 0 volts. But remember, it's 3 times higher in frequency. So as you go up quarter wave, right about here, about 5 inches now. It peaks. At 5 inches, it peaks. But then beyond that, it goes back down. It's back down to 0. And you're here, you're at about 10 inches or so. And then if you go another quarter wavelength, another 5 inches, wow, it peaks again. By the way, different phase, but it doesn't matter. It's in the opposite direction, but it peaks. It peaks. Which means what? High voltage, low current must be a high impedance point. It feeds right into there. So it feeds right into there. So that's good. But then what does it do? It wants to see 1/2 wave. It doesn't want to see more. More is not better. I used to think that my kid, longer the antenna, the better. Only if you've tuned it right. But not if you haven't tuned it right. It's worse. It wants to see a 1/2 wave at UHF. What's that? About 12 inches, 11, 12 inches, somewhere out there, depending on what frequency you want to tune to. So it wants to see this 11 1/4 inch piece, and that is it. It's got to stop. Because you know why? In a regular J-pole, it doesn't stop. It sees the current. I want to stop at 12 inches. If you cut it off, it works fine. Now you can't cut it off here, because if you cut it off here, it works fine at UHF. Now you can't get VHF, because VHF wants to see 37 to 38 inches. So what happens at UHF here? It wants to see about 12 inches, but it isn't broken. The current continues. Problem is it continues out of phase. It's in the wrong phase at that point. That's why you get cancellation. So you've got to stop it, otherwise you get cancellation. And then the waveform starts bumping up into the sky. So how do you stop it? Exactly like what I was saying before. Quarter wave stop. In RG174, the velocity factor, in other words, how much it slows down the speed of light, is quite a bit. It's only about 0.7, 70%. It slows down the speed of light in RG174 coax by about 30%, which means you say F equals F lambda, C is equal to F lambda, well, then it won't be 6 inches anymore. It'll be about 4¼ inch for UHF. You make the stub at 4¼ inch, that would be at UHF. It's shorter than it would be in air because of the velocity factor. You short it on one end, DC short to center conductor. Therefore, it's got to be a high impedance there, only at that UHF because it's 4¼ inch. Where is it a high impedance? 4¼ inch, you work it out of the Smith chart. Oh, at 445 megahertz. Great. Because then electrically, it doesn't see it. You don't want to see it. You just want to see, what, 12 inches or so for VHF. Now, UHF. At VHF, no, that 4¼ inch is meaningless. It's not resonant. You just add it virtually. You just add it the 4¼ inch to this whole length because at VHF, the whole length is 11¼ 4¼ 17. And what is that? I think it's 37 or something like 37 and a half, whatever it is. It's 37 and a half. Halfway. It works great on 2 meters. But 2 meters, it goes all the way through. At UHF, it runs in a wall. It traps it out. So therefore, you get pretty good patterns on both VHF and UHF. And it works, but what people don't realize is this, and now I heard from Tom Schiller, I see why. I always knew that we were very careful about our antennas and our materials. Because if you look at this 300 ohm twin lead we use, it's custom for us, custom made for us. Number 16 gauge and 18 gauge wire, thicker than that old TV Radio Shack stuff. It's got windows in it. The plastic is a special plastic with lower dielectric losses. But we have to order like 20,000 feet at a time for them to make it. I'll tell you a little story later on about the RG174 too. People say, why do you use RG174 in that roll-up? Isn't it lossy? I got a story. We played around with the vendor. I said, what's your lowest loss cable but super light? He goes, well, if you want low loss, can't be super light, right? You can't have both. He says, except we do have something you can try out. They send me a sample. I go, that's pretty good cable. What's wrong with it? They told me the story, and it's what I'm using, but there is a little catch to it. If you ever buy, I'll show you a picture of it.
Yeah.
This cable here, if you already have that for a DBJ2, and you put it on a network analyzer, hey, that's pretty good RG174. In fact, that's the best RG174 I've ever seen until you splice it. So they told us this, and I said, oh, we'll take our chances. The cable is not braided. You know, the ground usually is braided because then you can bend it forth and it's still. When you braid it, it kills the high frequency response. This cable is straight stranded cable, not woven, straight. And then they put a little bit of adhesive glue every 10 centimeters or so. So what it says, you can't be twisting the back. It'll start clumping, right? When it's woven, it won't clump. It'll start clumping and then it'll lose its shielding properties. But you have to actually do quite a bit. You got to do quite a bit of it. So overall, if you're careful with it, it works fine. It works fine. So we just ordered that. So you'll find that our cables are very low loss. It's very meticulous. And then the other thing we do is we use all copper. All copper. Tom Schiller says use all copper. I've never measured it. I know it seems to work well. He actually quantified it at different frequency. So whenever you're building dipole antennas, use copper. It definitely works better. It doesn't match any better, but it works better. So that's our RG174C. So this is the roll up. We put it all in one twin lead, and then we put heat shrink tubing on it. So we have little cuts to make it resonant, and it works well. Yeah, it works pretty well. So I'm going to stop for just for a moment. So did I get this concept correctly? Did you guys understand how we did this? It's a short at UHF, but it's an open there. So therefore, when a UHF signal comes through, it only sees electrically electrically that piece, which is what it wants to see, halfway. Does it? Raise your hands if you kind of get that concept. Oh, good, good. Yeah, okay, okay. Yeah. That's the trick to it. There's no capacitors, no special inductors. You've got to keep an antenna to that. I mean, when I open up an X200, that's the other antenna we like to open. Apparently a lot of people use them. X200, it's got two capacitors in there, ceramic capacitors, a 6 picofarad one and a 4 picofarad one tapping the coil. Well, no wonder you need a bunch of elements for gain. You lose half of your signal from those caps. You can't. Ceramic caps? Put that on a network analyzer at UHF. They're lousy. And all of a sudden, now they have to add extra ones to make up the gain. In the end, our antenna is just made very carefully. You put it in the air, you measure it, put an X200. Miraculously, they perform about the same. And you say, how can that be? We're basically a single element, and they're 258s at VHF and 458s at UHF. But it's because they use stainless steel. And they use capacitors. They got to hire Tom Schiller as their consultant. That's all I could say. If you want to go through. And Tom's a really sharp guy. He just, loves to give talks at PacificCon for us, our conference. But intuitively, some of the things he says, I mean, I just, the other guys, do you guys know John Portune? W6NBC? Publishes the QST a lot. And he'll give talks to you guys. Contact him. He'll love to give you a talk over Zoom. He's a real practical engineer. He's retired, so he does all these experiments that I don't have time to do. Although I should just give these as master's projects to my students. But he comes up with, what type of PVC pipe to use to cover up, and then they're not all the same. Turns out that mine is second best. He had a talk. In fact, he had a talk to our club about this. Here's a different, because you have to cover up an antenna if you want it to last long. Especially if it's made of copper, it's going to oxidize, right? If you want to use copper, you got to cover it up. And he goes, here, I did a bunch of tests on all this stuff. All these manufacturers of PVC from Home Depot, Charlotte, to a bunch of them. And I go, wow. Because I kind of, in our antenna, we use 23990. I tried different ones, and it wasn't a scientific test because it takes quite a bit of effort to actually set up a situation. You're testing. I guess I could have made it into a master's thesis for some of my students, but I didn't. To try this PVC, and then you actually have to make real field tests. It takes a lot of time, but he did it, and I was really surprised. Well, wow, mine was like number 2. I should feel really good about that because I didn't do any. I did very minimal. I did on the air tests. It wasn't like with meters and spectrum analyzers and like that. And then you ask, I bet you guys said, so if he was number 2, what was number 1? Well, PEX pipe was number 1. That blue PEX pipe was the best. There wasn't that much difference, but you can't use PEX pipe. It's too flexible, way too flat. It's designed to be bent around corners, and so it's not practical unless it's for UHF really short. But I think that it's a practical pipe, inexpensive practical pipe. The Lowell's 23990 seems to be the best so far. That's what we use. So anyway, let's see. Okay, so I mentioned that the 2 dimensions are different. One goes into 23990 for the base station. And of course, the roll-up one that's here, you just hang on a tree, and then here's the coax, and it does 2 bands. But that doesn't have a cover. It doesn't have that PVC cover, which means it's going to be longer, right? It doesn't slow down the speed of light. It is. This roll-up that you hang on a tree is about 2 inches longer than this one that's designed to go into a PVC pipe. So it's enough where you just can't substitute the 2. People say, well, why can't I have a roll up, and then when I want it as a base, I'll stick it in the PVC pipe? It doesn't work. It's about 2 inches off. Okay, so here's an actual, what did I use? 8591 spectrum analyzer on here, and yeah, it works. Here we are, our 2-meter J-pole at UHF. That's a reference right here. Standing in the same spot at a parking lot, it was like 50 yards. I did this years ago. Sure enough, you replace it with mine, boop, it comes right back up about 6 dB. That's a lot. That's like 4x. That's your 1 watt HT turns into a 4 watt, or you can look at it this way. Here, you start with 4 watts and you end up with equivalently 1 watt. Wrong way to go. That's not the way to go. So, and then you wonder why I have this data. I have this data, and let me explain it to you. It's because one of my master's students wanted to know, how hard is it to test how an antenna works? Good, I've got the one exactly you want to test. And he looked it up in the National Institute of Standards and Technology, how you qualify a real antenna. You gotta have a spectrum analyzer that's NIST calibrated. You gotta have a signal generator that's NIST calibrated. NIST is NIST, National Institute of Standards and Technology. And then they say for an antenna, you have to test on a rainy day and a foggy day and on a sunny day because the measurements will differ. So I said, why don't you do that for your thesis? Since you run out of ideas. It seemed like, hey, it seems like he was going to have fun. So I said, go ahead, have fun and get your master's degree with this. So here's kind of his results. If you take a VHF mobile antenna, quarter wave whip, as a reference, minus 24.7 dB, and it was a generator in about it was in a parking lot at school, probably a little bit more than 50 yards, maybe. Just as a reference. The idea is you can use anything that's clear that's not going to change during your measurements. So you got to do it on a Sunday, right? You can't have people moving in and out of the parking lot. This is a Sunday. It was very quiet. We did this, and so minus 24.7 dB reference. Ooh, I should get a large B there. Use a rubber duck. Lousy. Minus, lose about 6 dBs. All of a sudden it's minus 30. Use a VHF J pole. It's all of a sudden gains about 1.3 dB or so. It is better. A VHF standard even measures better than a quarter wave. I mean, it's like 1.5 dB. Not night and day, but it's measurable and probably audible in a weak signal. And then use our J pole. It's about the same as a regular J pole. It loses maybe 0.1 dB at the most. That's negligible. That's because that little stub you put in there, it's a little lossier. But let's check it out at UHF. At UHF, the same situation, just a reference signal, minus 38.8 dB. You put a rubber duck in it, not too bad, minus 41 dB. And you say, well, why is that the case at UHF? Well, obviously at UHF, that rubber duck you're using is a good one, is about 6 inches, 5 or 6 inches. It's already a quarter wave. It isn't resonant because you don't have the other end, but it's, as opposed to VHF, it should be about 18 inches, and a rubber duck at VHF is only about 6 inches. So it's really compressed, and you pay for that. You pay for it in gain. It does lose quite a bit more. 6 dB here, 3, maybe 2, 3 dB here. So it does work better relatively. The UHF works better with its rubber duck. Now here's where it really shines. Use a standard VHF J pole at UHF. Not good, like what I said. The reference of the quarter wave mobile antenna was 38.8. It drops to 45. So again, over 6 dB. Like 5. Oh yeah, over 6 dB, 6.2 dB. 1/4. You lose 75% of your signal, approximately here. But theoretically, you lose 75% of it because it goes up into the sky. And you want to bring that back. And sure enough, you use our little technique here, a simple piece of coax. You got to just know what you're doing, tune it just right, and you get it back up to 38.9. So you almost get it all back. So that's about it. See, here's our instruments here. This is taken in 2008. This is our 8753. So we live in real luxury now. That ran my lab $88,000. Color screen, didn't have USB, had a floppy. Good instrument, no doubt, good instrument. This is just as good of an instrument, but it's more automated. It's a Keysight 5062, runs about $48,000 now. Really PC based. It's almost all PC. It's a whole PC computer in here, and just this whole panel of all the measurement devices, the specialized ICs, and all that. And it's about a little while. It's under 50. But here I stand next to a nano VNA. I swear. I don't tell anyone this. I don't use this anymore. I don't even use this anymore. That one's stored away. I don't even need to use this only when you're doing like a scientific report, where everything has to be calibrated to NIS standards. Not just sure. But more just playing around most of the time. Believe me, the antennas you buy from me are not tuned on a 5062. It's tuned on a little nano. It's fast, it's battery operated. You can't beat it. Under $100. But that's why all of you guys have it. Then of course it's quite a learning curve, right? It could do filters, it could do amplifiers, it could do matching of antennas. There's all kinds of cool things for $100. Oh, last thing. So that stub, I added that stub. That's the mystery. How good is that stub? Well, it is not perfect, but it apparently does work. So I said, someone says, "Well, put it on a network analyzer." This is a 8750. This is 8753. This is an 8753 a while back. It should sit out way here at 445. It doesn't. It's not quite infinity, but it's a lot higher than 50 ohms. Let me tell you that much. So it does act as a trap. Not perfect, but you'll find that that's always the case with coaxes and things like that. In engineering, it's never going to be perfect. If you wait for something to be perfect, you'll never finish it. At some point, you got to just meet the spec and you go with it. And I find that point is pretty stable. I put my hand around that stub. Yeah, it shrinks and all, but it still stays pretty stable because it's resonating. Here was a piece of wire, just a pure wire at that frequency. Pretty much an open circuit right there. So this open wireless. Oh, I said 146 marker of the UHF shorted stub. Oh, that's a shorted stub. I see, and that's the wire. Yeah, if I remove the stub, put a wire there, it's all pretty high. It looks like the wire's a little better. I would expect that. And again, I like this idea of this J pole. It's tall. It's 3 1/4 wavelengths. But again, when it's vertical like that without radials, it's only vertical force. There's no horizontal force, so it holds up really, really well. And the example I give is just grab one of these antennas I have here. Just grab one of these antennas here, or PVC pipe. I can hold this up vertically really easily. In fact, I can hold it up with a finger like this, if it's vertical. But if you have radios, anything horizontal, you have horizontal gravity force. Much harder to hold up. Much, much harder to hold up. And over time, if it's something in a mountain, it makes a big difference. These things you really got to consider. Having no radials for antenna that you want to last. You rather have a taller antenna all vertical than a shorter antenna with radials. I think that's my conclusion. And you can see these in these photos. Nobody uses radials and it costs you too much to climb that tower. So here's a kit we offer. This is that roll-up one. It comes with the adapters for BNC, SMA female to reverse it for Balfour. It comes with a custom extension cable. That's that RG174 I was telling you about. Thin, but really low loss. Not the most rugged in the world. But we have it custom made with a male BNC and a female. So this one just goes in there. You want to extend it. So we do this as a fundraiser. That's how my group makes money. Let's see. Okay, so other talks include this. How do you actually get gain out of J-pole? Pretty interesting stuff we've been experimenting with. And how you get tri-band, 2-meter 224/40. Right, talk on that. Well, that's just some radios that I think are pretty cool. These Chinese radios, we've been trying them out because they're so cheap. They actually work pretty well, surprisingly. I kind of show this. This is my mountaintop radio. USDX, the one that's done by the Northern California QRP Club. Really cool. I mean, I didn't have anything to do with this except play with it. All band, all mode, even has a CW decoder. It's done in an Atmel 3200, SDR software defined chip. And the batteries last forever on single sideband. Puts out about 5 watts. So like California QSO, I hike up with my daughter to the hills or spend a couple of nights, and we make a lot of contacts. Lots of. By the way, the only thing I don't like about backpacking with a radio is when you operate a radio, you like to be sitting in a chair or the desk, blogging. Boy, you do 2 days of no chair and sitting on rocks. It's really uncomfortable. I tell you, someone said you got to look into these carbon fiber portable chairs. Not cheap, but apparently they're really light. Oh, you guys try to operate. If you operate at home, you always have a desk and pen in it. Oh, sure, but you try to operate without a chair. We did California QSO, and then you can kind of blow up your mattress because I get a little blow up mattress. But then you're kind of laying on the side. You just never can get comfortable. Nothing is more comfortable than a chair and a desk to operate contests. So I think that's why we limited it to about 70 contacts. We got to Canada. Alberta and Saskatchewan, Alaska. We got all over, but you just can't keep on operating. It's too fatiguing. You're basically your butt really sores afterwards sitting in a rock. It's not fun. I mean, you can do it for a few hours, but after the third day, I need a chair of some kind. But it's fun. And here's the radio inside. It's really cool. With coils, and see the whole radio is based on a microprocessor or a programmable FPGA. The display. Oh, here's the finals. It's a switching RF amplifier. Uses BS 170s. I mean, these guys in Northern California QRP Club, they really know their stuff. They really did a good job on this. It works out well. A little speaker, for $150. It's just lots of fun. And I for HF, I got a 83S beam, and I used to use Collins S line, but I use Drake and Yaesu stuff, and I guess when you've been doing it for 55 years, at 100 watts, or then you turn on your linear, little under a kilowatt, you can literally talk to anyone you hear. But it becomes all of a sudden fun. How well can you do on 5 watts? Then it's all on your antenna and losses and things like that. So it's pretty interesting. Anyway, that's the end of the talk, and we sell these antennas. I can email Robert or Steven or somebody. So when I give a talk to a club like you guys, I'm sorry if you guys already have my antenna, you bought it retail, because you get it at 20% off as a club member. No refunds, you guys that bought it retail. Sorry. But if you want to buy them now, $38 as opposed to 55 now. And the roll up with all the accessories, the cable and all the adapters included, 40 as opposed to 60. The tri-band with the shipping and everything is 90. It would be 65 with shipping and everything to you guys. So about 20 to 30% off. And we also offer a GMRS gain antenna, the gain one I was telling you about. Normally we sell it for 65, and we do it for 43. And then the extensions are the same in the accessories. So I can send you guys a spreadsheet. You guys just fill it out, take your time. Then you support my group, and then we just send everything in a box, or a couple of boxes, depending on how much you order. Okay, so, and you can always ask questions about this. But back to the antenna. So any questions on that?
Hey Ed, my name's John, N6VG. I did pick up your tri-band when I lived in California. Question, how high up can I mount against a mast the base of the antenna so that I don't interfere with its performance?
How high up?
In other words, is there a distance at the base of the antenna where I can mount without...
Oh, the bottom. Oh, it's
Yeah.
like 12 inches. 12 inches.
12 inches? Okay, because I've seen numbers between 8 and about 16.
Yeah, probably be safe 8 inches. Okay.
Okay.
It's plenty of space, 8 inches. But always use 2 clamps, right? The physics of it. You use one clamp that's all torqued in one spot. You use 2, it really holds it tight.
Okay, we'll do that. Thanks.
And remember, you don't need a lightning arrestor on these things. It's a DC shorted antenna. It's got that short on the bottom. And people used to ask, it's a short circuit, how can it work? It's a DC short. It's not an AC short. Obviously, at 145, 146 megahertz, it's 50 ohms because it moves up at an inch, an inch and a quarter to tap. That makes it at VHF and UHF about 50 ohms. So don't buy a $50 lightning arrestor. You don't need it. Tell them that Ed sent you. You do not need to spend an extra $50. I had a big write-up paper at ATD Alarms. They had been using ground planes previously. So you need a lightning arrestor for every antenna because ATD, they have a mesh network these days in cities for fire and burglary. And I'm saying, why are you guys doing this? You buy a DC shorted antenna. That's what a lightning arrestor does, right? At a certain voltage, it shorts a gas, or they use something, it shorts out to discharge it. We're always discharging it. We're DC short. And finally, finally found an engineer that understood what I was saying. Because you're right. Why would you need it? You don't. You can save $50 on every antenna you put up on the roof. So no lightning. I mean, you should ground it, but it's grounded to your radio automatically from the shield. And then they said, well, would it arrest lightning? I go, no, it won't arrest lightning. Nothing would arrest lightning. Right? If you and I can invent a lightning arrestor, which I don't know how that term got accepted, we're God, right? If you and I invented something in arrest lightning, we'll be multimillionaires. Think about the billions of dollars of damages done every year. So I explained what a lightning arrestor actually does. It does not arrest lightning. It's just that when a lightning occurs, storms around you, the wire in your antenna can induce, right, like through magnetic induction, because there's millions of volts in a lightning bolt. Even if you induce a fraction of that, 40 volts, which would be like 0.01%. If 40 volts runs down through your antenna into your radio, there's a good chance it will burn out the front end. I've had that happen. That's what a lightning arrestor does, right? At some threshold, the gas shorts everything out. But how about if you just design it out? You say, what's a short circuit? Any induction of a signal, it just goes to ground anyway. Then you don't need a lightning arrestor. So, any other questions?
Hey Ed, Jeff
Yes.
Lamar, KD0SMQ.
Yes.
I was wondering, when you designed your tri-band antenna, when you did the test where you compared the gain of your antenna to the gain of a quarter wave and a rubber duck, if you saw any appreciable difference on the 2 meter and 70 centimeter with the addition of the 220 megahertz?
No difference. No, it's
Nothing.
in parallel. There's no difference.
Wow.
No difference. But like I said, the thing that amazed me the most is people started using this stuff and says, your antenna works so well and it's so simple, but it compares an X200. So we start buying X200s, trying to figure out that can't be. It is, because the materials they make it out of. Again, Tom Schiller says, you gotta make all your coils and your radiating elements in copper, not stainless steel, not chrome, not aluminum. Those are terrible materials to use for ACRF antennas. I got to start testing some of that. We've got all the instruments here now, because I knew copper was good, but I didn't. But this last meeting at Pacific Time, he actually showed charts. He built dipole antennas out of aluminum, out of stainless steel, chrome. I'm surprised chrome, because we use those on CB antennas when we were little. Not a good material. In fact, what he did do in one experiment was he took a whip antenna and covered it with copper tape, and boom, showed the performance. Like 4 to 6 dBs. I'd never seen data like that. Anyway, thank you very much for your time. It's probably getting late there. I've got other lectures. If you're always caught up on something, whoever organizes these talks, I know how it is. Caught up. Hey, I don't got a guest speaker. Let me call Ed, okay?
Yep, we will definitely be in touch with you again.
And if I'm available, sure, I'll throw some kind of talk.
All right, well, thank you very much.
I've got enough in
This
my
was
pocket.
great.
You're
Thank
very
you.
welcome.